Hi, my name is Fabio. Welcome to my video project about rheology and its basic properties. So, in this video we will see some basic concepts of rheology and some rheological behaviors in the last curious of diverse materials. So, what's the rheology? Rheology is the science that studies the deformation and flow of solid or fluid bodies, gas or liquids. But what's the importance of rheology? Rheology is very important in different areas of industry, including production, transportation, distribution, and application, among many others. For example, in the pharmaceutical industry, we will need to know how the products will flow into the skin, like we can see in this picture. First, let's understand the rheological behavior of matters. We can divide the matters into liquids and solids. Solids don't flow, have a defined size and shape, while fluids flow and have a defined size but doesn't have defined format. But this is not a for scientific definition for these materials. In the real world, materials are more complex, like shampoo, toothpaste, and tires. These materials cannot be simply defined by two words. So, how can we better define these materials? The answer is through rheology. Rheologically speaking, many of these materials are viscoelastic, which means that these materials have a elastic and viscous fraction. With this link, we can approach the first rheological term, that is deformation. With this link, we can approach the first rheological term, that is deformation. Deformation happens when we apply a force on a body and it changes its shape. For example, when we apply a force on top of this body, he inclines deformation. In addition, this deformation can be reversible or irreversible. In irreversible deformation, if we withdraw the force be applied on the body, it doesn't return to its original form. Play the irreversible experiment. But in the second case, in reversible deformation, for example, in one experiment with elastic, when we apply the force, the elastic deforms, but when we take this force out, it returns to its original form. This happens because the elastic has a cross-linked structure that keeps and recovers the material's original form. Play and see the experiment reversibly. Second term is viscosity. It is a physical property which characterizes a resistance to a flowing fluid at a given temperature. The more resistant a fluid is to flowing, the more viscous it is. For example, In this experiment, we can see that water has a lower viscosity than running and the shampoo, and this is the reason why it is flowing faster than other. However, viscosity can change with the matter properties like weight or environmental conditions like pressure and temperature. Plate temperature. In this experiment, we can observe that when honey is heated up, his viscosity reduces when compared with the same but with low temperature. Other term is fluid. It's a measure of product thickness. It is the inverse of viscosity. We can see it better in the equation where mi is the viscosity. With this, we can argue how viscous a material is by how thin he is. So, shear stress. Shear stress, in his definition, is the force applied per unit of area. Shear rate is a difference in velocity between liquid at the outside of the pipe and the middle divided by the relative distance. We can correlate the stress and the shear rate by this equation, where stress is equal viscosity versus shear rate. The graphic stress per rate describe different fluid behavior, such as Newtonian and non-Newtonian. Newtonian is a fluid with viscosity doesn't change given a shear rate and time. For example, water, when you apply a force, the viscosity doesn't change. Non-Newtonian is a fluid with viscosity change given a shear rate. For example, cornstarch. With water in normal condition, it is presented in liquid form. However, when it's applied a force, this substance is presented in a solid form. Now we will see some interesting effects of non-Newtonian fluids. First, it is dye swell. In an instance where a polymer stream is compressed by entrance into a dye and is flowed by a partial recovery of swell back to the form, shape, and volume of the polymer after exiting the dye, hence the term dye swell. Its phenomenon is relevant because it controls the size and shape of the extruded product, determining the extruded products associated with the occurrence of the shaking skin and melt fracture. Play and see the experiment. The dye swell can be altered by resistance flow, time, dye temperature, shear rate, dye legs or dye length, molar mass, flow patterns, dye geometry, and many others. Second is a Weisenberg effect. It's an alteration of the normal stress in a non-Newtonian fluid on account of elasticity, so that such a fluid, when placed between two concentric rotation cylinders, can rise on the inner cylinder in the speed of centrifugal force. Last but not least, K effect. It's happened when an organic viscous mixture is poured into a surface and then a small part of it pulled, merging with the pouring liquid.